Hello guys, and welcome to another calculus video. Today we're going to be checking out these two cool, I guess the word for them would be functional differential equations. So they can't be solved entirely using normal differential equation methods because obviously we have this negative x in here, so we can't, it's hard to express in terms of y, right? So we're going to take a look at this one first, and we're just going to solve it using two different methods, and then we're going to go ahead and solve this one. So let's jump right into it. So the first thing I thought of when I saw this first functional differential equation was that because we just have x and it's not shifted over by anything, it's just multiplied by -1, we can convert it into a power series, and that is the first solution that I used to solve this differential equation. So let's go ahead and do that. So let's let f of x equal the sum from n equals 0 to infinity of an x to the n. Then f prime of x is sum from n equals 1 to infinity, because the first term is going to disappear since it's a constant, of an times n x to the n minus 1. And on the other side, we have f of negative x, well, which is a sum from n equals 0 to infinity of an negative 1 to the n x to the n. Next, we're going to shift the index on the left side, so we're going to add 1 to n everywhere. So this is going to become n plus 1, n plus 1 times x to the n. Then, since we have these sums on both sides with the coefficients of x to the n, all we have to do is equate the coefficients, and hopefully we'll be able to figure out what this function is. So the coefficients here, we're going to have n plus 1, n plus 1 is equal to an negative 1 to the n. Alright, so now the tough part here is dealing with this n plus 1 that's sort of sticking out here. It's going to make it a little bit difficult for us to figure out, right? So one cool trick that I have found out is we can substitute an with another function. So when we see n plus 1 times an plus 1 equals an, I can kind of see that if I was dividing by some factorial, then multiplying by n plus 1 would kind of cancel with the factorial, right, and would bring me to the term before. The same way, if I had n times an equals an plus 1, that would remind me of the factorial function. In this case, it's just backwards, so I probably have a reciprocal factorial. So I'm going to make a substitution, say that an equals some other function, or some other sequence, I guess, bn over n factorial. And so that's going to allow me to substitute everything in here. We have n plus 1 times bn plus 1 over n plus 1 factorial is equal to bn over n factorial times negative 1 to the n. And you can see that this cancels with this to become n factorial, so that also cancels on the other side. Another way we could have done this is at the beginning, if we instead just had this over n factorial right here, and the way that Taylor series would generally look like, but we dealt with it now. So now the easiest way to do this, since we have this negative 1 to the n, is to just start plugging in numbers until we notice the pattern. So since every term depends on the term before it, we can pretty much choose any value. I'll call it c, or actually I'll just choose 1 for now for our term b0, and every term after that will be dependent on b0, right? So if we assume b0 equals 1, then b1 is just going to be 1 as well. And that's just plugging in n equals 0 right here. Then if we plug in n equals 1, we're going to find that b2 is going to equal negative 1. And if we plug in n equals 2, then we're going to find that b3 is going to equal negative 1. And now the sequence is just going to repeat. So we have b4 equals 1, b5 equals 1, b6 equals negative 1, and b7 equals negative 1. So I'm just going to go ahead and make some more space here. So since we've noticed this pattern, it's actually kind of hard to define a super easy function that takes on these values. But one thing that we can notice is that if we look at all the even terms, they alternate, right? And if we look at all the odd terms, they also alternate. in sign. And so we can just write these as alternating series depending on the even and odd terms. So one of these series, so f of x, is going to equal some constant. So this constant would be, I guess I'll just write it. It's going to be b0 times these series. So we can choose any number we want for b0, since obviously if we multiply f of x by some number, it's still going to satisfy the differential equation. So if we look at the odd numbers, so from n equals 0 to infinity, we're going to be looking at x to the 2n plus 1 over 2n plus 1 factorial, right? Just picking all the odd numbers out of there. And of course, if we look at our first term, when n equals 0, that's b1 right here. And so we're just going to have 1, and then negative 1, and then 1, and then negative 1. So that's going to be negative 1 to the n. And inside of this same parentheses, we're going to also have the even numbers, which is going to follow the same pattern, negative 1 to the n, x to the 2n over 2n factorial. And hopefully you guys recognize these two series as sine of x and cosine of x. So our function f of x is actually equal to b0 times cosine x plus sine of x. And we can go ahead and plug in f prime of x, which is going to be b0 times, that's an integral sign, times negative sine of x plus cosine of x. And we can also look at f of negative x and see that this does indeed match up, because we're going to have cosine of x minus sine of x. So that, I think, is a pretty cool solution to a functional differential equation, but I have an even cooler one on the way. So one thing that another thing that I thought of once I looked at this problem a little bit longer is the properties of even and odd functions. So obviously, this is closely related to even and odd functions, since we have, f of x and f of negative x. So I was thinking I could manipulate some properties of those functions. And I remembered an interesting property of functions, or I guess an interesting trick that you can do. You can deconstruct any function f of x into an even function and an odd function. So there's an even part and there's an odd part. And you could do this pretty easily by splitting up the power series like we did last time, or by simply taking e of x equals f of x plus f of negative x over 2, and o of x equals f of x minus f of negative x over 2. It's pretty easy to see that e of x is an even function and o of x is an odd function. So I'm going to split this up into these two functions, and I'm going to go ahead and solve for these two functions using our differential equation. Now there's one other thing I want to quickly prove, and that's that the derivative of an even function is an odd function, and the derivative of an odd function is an even function. So it's super easy to prove. So for e of x, we know that e of x equals e of negative x. This is just some arbitrary even function, so this holds true for any even function. If we differentiate both sides, we see that e prime of x equals negative e prime of negative x, which essentially tells us that the derivative of an even function is an odd function, since we have these negative signs right here. And we can do the exact same thing with an odd function to show that its derivative is an even function. All right, so let's go ahead and apply this to our differential equation. So we're going to end up with e prime of x plus o prime of x here. And f of negative x is going to be e of x minus o of x, because o of x will be negative because we're looking at negative x, right? And notice that e prime of x is an odd function, and o prime of x is an even function. Here we also have an even and an odd function. So we know that these functions will match up because you can't split up an even function into multiple odd functions, or an odd function into multiple even functions. So they have to match up exactly. So this tells us that e prime of x equals negative o of x, and o prime of x equals e of x. Again, o of x is the odd component, and e of x is the even component of f of x. And so we can just take either of these equations and differentiate it, and we can find that e double prime of x is equal to negative o prime of x. But as you can see here, O prime of x is just equal to E of x. So we can go ahead and say that E double prime of x equals negative O of x, or negative E of x, sorry. And we'll say that E of x equals y. And this is just this ordinary differential equation right here, second order, linear, homogeneous. So y double prime plus y equals 0. To solve this, we'll just set y equal to e to the ax. And we'll find that a squared e to the ax plus e to the ax equals 0, or a squared plus 1 equals 0. So a is I, or negative I. Well, and negative I. And so we can reorganize, since we know that y is going to equal c1 e to the ix plus c2 e to the negative ix. We can also write this as c3 sine of x plus c4 cosine of x. However, we're looking at e of x here, and we know that e of x is just an even function, so it can't have this sine of x here. So that tells us c3 is 0, so it's just equal to c4 cos of x. So we know that e of x is c4 cos of x, and from the last slide we also have O prime of x equals e of x. And so since we know what e of x is, we can just substitute that right in. And after integrating both sides, we find that O of x is equal to c4 sine of x plus c5. Now the interesting thing here is we know that O of x is an odd function and sine of x is an odd function, but c5 is unfortunately even unless it's equal to 0. So we know that c5 is going to be equal to 0 in order to make O of x an odd function, which we know that it is. So we have e of x as c4 cos of x and O of x as c4 sine of x. So that tells us that f of x is equal to c4, which again is just an arbitrary constant, cosine of x plus sine of x, which is the exact solution we arrived at before. So I think that's a pretty interesting problem. But the next one is actually going to be a lot more fun to deal with. We get to do some more integration and actually come up with a much more interesting function, because we always see cosine of x and sine of x when we're doing differential equations, but we're going to get to see some more fun functions in a moment. So this is our next functional differential equation. We have f prime of x is equal to f of x times f of negative x. And this is an interesting case because here we can't apply the power series because we would have to multiply those power series together, which I think is possible, but I have no idea how to do it, to be honest. I mean, it's probably possible to figure out what terms multiply with one another, but again, it would be just simply too difficult to be a real option. So instead, we are going to use the second method, and we're going to split up f of x and say that f of x equals e of x plus O of x again, and even part, odd part, right? So f prime of x is going to equal e prime of x plus O prime of x times e of x plus O of x times e of x minus O of x. All right, and luckily here we have a difference of squares relation, which means that we can just say that e prime of x plus O prime of x is equal to e squared of x minus O squared of x. And the interesting thing about the right side here is that the right side of this equation is a completely even function, because we have O of x squared right here, and O of x squared, when we plug in negative x, we're going to get negative O of x all squared, and that's just going to end up being O squared of x positive again, because we're squaring a negative number, right? So both of these are going to be even, which means that our e prime of x, which we know is odd, is equal to 0. So e prime of x equals 0, which means that e of x equals c1. So we can go ahead and plug that into our equation. We're going to end up with two very different situations here, depending on if c1 is 0 or not. So first, let's look at the case where c1 is not equal to 0. O prime of x. So again, e of x equals c1. So we're going to have c1 squared minus O squared of x. I'm just going to convert this into y notation so that it's easier to look at. Y prime equals c1 squared minus y squared. And this is just a simple first-order separable differential equation. So we're going to have dy over c1 squared minus y squared equals dx. We're going to integrate both sides. And this is actually a really interesting integral. You can go ahead and do partial fractions if you want on it, but I'm going to instead use the inverse hyperbolic tangent function. And you can go ahead and check my work, and you will see that it does match up. So it's kind of similar to integrating with arctangent. We're going to end up with 1 over c1 inverse hyperbolic tangent, sorry, of y over c1 is equal to x plus c2. We're going to go ahead and multiply by c1 on both sides, so I'll just make this c3 and then c1x. Then we're going to apply a hyperbolic tangent on both sides, so we're going to get y over c1 is going to be equal to tan h of c1 x plus c3. And we can just bring that c1 right there. So again, this y was equal to O of x originally. So now we have an expression for O of x. Something that I do want to note here, however, is we have this plus c3 here. If you're familiar with the hyperbolic tangent function, it is an odd function. And it looks essentially like inverse tangent actually, so it looks something like that. The problem is, if we shift it over with that c3, it's going to look like this, something that's not necessarily an odd function. So we actually need c3 to be equal to 0 in order for this to be odd. So I'm going to go ahead and just remove c3 because c3 is equal to 0. So this is our solution. O of x equals c1 hyperbolic tangent of c1x, and E of x equals c1. Now let's go ahead and show that this does satisfy the differential equation, and we'll also go ahead and see what happens if c1 equals 0. So let's go ahead and plug that into our equation. So on the left side we have f prime of x, which means that E of x is just going to disappear, and we're going to have c1 squared hyperbolic secant squared of c1x. That's just the derivative of hyperbolic tangent. And on the other side, we're going to have c1 plus hyperbolic tangent x, c1x, and c1 minus hyperbolic tangent x, c1x. And so we're just going to end up with, here I'll just do this like this, c1 squared minus tan h squared of c1x. Oh, I forgot the c1 in front here. So when we factor that all out, again, we have a difference of squares relationship. So we're going to just have c1 squared times 1 minus hyperbolic tangent squared of c1x. And one of the fundamental hyperbolic trigonometric identities is that this is equal to sec squared of c1x. And you can see that that perfectly matches up with what's on the other side, indeed confirming that our differential, that this is a solution to our differential equation, functional differential equation. However, there is another case we have to take into account. Remember that we had O prime of x equals c1 squared minus O squared of x. However, if c1 equals 0, then we have O prime of x equals negative O squared of x, which is a little bit different from what we had before. So if we go ahead and solve this, we're going to get, setting O of x equal to y, we're going to get dy over negative y squared equals dx. We're going to get 1 over y is equal to x plus c2, right? Just integrating. And we're going to get that O of x equals 1 over x plus c2. But again, we can see that 1 over x is a perfectly odd function, but if we shift it over, it's not going to be quite so odd, right? So we actually do need c2 to be 0 in this case, and that means that O of x is just equal to 1 over x, and that is another solution to our equation right here. It's just a kind of a special case here. And we can go ahead and pretty easily show that it's true, because on the left side we're going to have negative 1 over x squared, and on the other side we're going to have 1 over x times negative 1 over x, which is of course the same thing. So that all works out. So this was kind of a different video. I've never really done functional differential equations before, but this was actually a lot of fun. I was surprised that it was relatively simple to figure out these answers, and I was glad to learn about even in odd functions and how they can actually be pretty helpful in solving these kinds of problems. So I hope you guys learned something, and I hope you enjoyed the video, and I will see you next time.